Hi everyone, this is Becky, and in this video we are going to take a look at solutions and molarity. So the goals of this video are for you to be able to describe solutions in terms of their composition and their concentration, and to be able to do calculations involving molarity units, so be able to work with molarity in all of its shapes and forms. So when we talk about solutions, right, remember that a solution is just a fancy word for a homogeneous mixture, which is just a mixture that is the same throughout, right? So a mixture that has the same composition throughout the solution, things like apple juice, no pulp orange juice, air, all of these, brass, all of these things are considered to be solutions. So when we talk about solutions, because these aren't pure substances, they're mixtures, we have to talk about the different components that are involved. And so if we have a solution, the component that's present in greatest amount, or the thing that does the dissolving, is said to be the solvent, and every other component is called a solute. So I could have a solution here, right? We typically draw this where we don't draw the solvent, but we draw the solute. So here, it's like that, right? And that's my solution, and that's all pretty. I could have more than one solute present in a solution. Think about something like salt water or ocean water, which has tons of different stuff in it. So it's got salt, it's got sodium carbonate, it's got sodium bicarbonate, it's got magnesium carbonate, air or CO2, oxygen, all of those things are present, and all of those would be solutes, but a solution can only have one solvent. There's only one component that's present in the largest amount. All right. Remember that solutions don't have to be liquids. They can be gases, they can be solids. So think about air. Air is a solution of gases. Think about brass or other metal alloys. Those are solutions of solids. You can have a gas dissolved in a liquid. State doesn't matter here. All we're talking about is a homogeneous mixture that has two or more components. Okay, so when we talk about a solution in terms of its composition, we talk about it in terms of its composition, so what is present, and then we have to talk about it also in terms of how much is present, right? Because salt water has different compositions. Not all saltwater solutions contain the same amount of salt, so I need a way to describe a solution that contains more solute versus one that doesn't. And so what we talk about is the concentration. And so the concentration of a solution is defined as the amount of solute per given amount of solvent or given amount of solution. And this can vary depending on the units that we're talking about, right? So for example, in the activity that we did in class today, you calculated the concentration of the solute in terms of moles of solute per liter of solution, right? We could also calculate this in terms of like thinking about grams of solute per liter of solution, right? I could have grams of solute per gram of solution. Lots and lots of different units are possible here for concentration. The one that we're going to use the most commonly is this guy here, which is so common it has a name, and it's called the molarity. So the molarity of the solution is equal to the moles of solute per liter of solution. And we use this unit so often it has an abbreviation. That abbreviation is a capital italicized letter M, which is read as molar. So molar means moles of solute per liter solution. So if I have, for example, a 6 molar HCl solution, that solution contains 6 moles of hydrochloric acid for every 1 liter of total solution. Okay, a couple of things to keep in mind here when we're talking about molarity. This is liters of solution. This is not liters of solvent. Remember that as you add the activity from today, as you added the sugar and the salt to the water, the total volume of solution changed because the solute takes up space. So keep that in mind. This is volume of solution, not volume of solvent. Okay, so molarity then becomes a conversion factor in doing dimensional analysis and working with solutions. So for example, if I wanted to determine the molarity of a solution that contains 10 grams of AgNO3 and 250 mils of solution, right? So I know my concentration right now. So about this is 10 grams of AgNO3 for every 250 milliliters of solution. And if I want this concentration to be in terms of molarity, well, okay, so I have to convert my grams to moles, and I have to convert my milliliters to liters, and then I have my concentration in terms of molarity. So For me, I like to set it up all at once and just kind of do it this way and do it in one big conversion factor or one big dimensional analysis thing. You can separate it and then divide. It's up to you. But I do it this way. So 10 grams of AgNO3 per 250 milliliters of solution. Easiest one to do right now is going to be to change the milliliters to liters. So I know that there's 10 to the third milliliters in every 1 liter of solution. So the milliliters cancel, and now I'm in units of grams of AgNO3 per liter of solution, right? I can use the periodic table to calculate the molar mass of AgNO3, which I do and find that it's 169.88 grams per mole. So I know that for every 1 mole of AgNO3, I have 169.88 grams of AgNO3. So the grams of AgNO3 cancels out. So unit-wise, I'm here in moles of AgNO3 per liter of solution. So that's the units that I want to be in. So then I just take 10, multiply that by 1,000, divide it by 250, and then divide it by 169.88. And I get my solution to have a molar concentration of 0.235 molar AgNO3. Okay. Significant figures wise, I need 3, 10 grams and 250 milliliters both have 3 significant figures, so my solution would be 0.235 molar AgNO3. Okay. I can also use the molarity as a conversion factor, as I have to do in this problem here, where I'm looking at the volume of solution that contains 6.35 grams of salt, right? So here, unit-wise, I'm starting out in grams of NaCl. And my goal unit here is going to be volume of solution, right? So my conversion factor wise, I convert grams of NaCl to moles of NaCl. And then from moles of NaCl, I can go to liters of solution here using my molarity, right? So I'm going to use my molar mass, and here I can use my molarity to get to liters of solution. So setting that up, 6.35 grams of NaCl, right, over 1. And I know the molar mass of NaCl is 1 mole of NaCl. Using the periodic table, this is 58.44 grams of NaCl per 1 mole of NaCl, right? And then I know that every 1 liter of solution contains 0.75 moles of NaCl. And then so the moles of NaCl cancel out, and I'm left in liters of solution, which is the unit I want to be in. So I would just take 6.35 divided by 58.44 and divide that by 0.75. And then so it would be significant figures wise, I need 2, so 0.14 liters of solution, right? So this is, again, very similar to the stuff that we've been doing before. It's dimensional analysis. It's just now we have this new unit conversion, this new unit that we have to think about in terms of concentration of solution. So think about this one. So I want you to describe how you would make 350 milliliters of a 0.125 molar solution of sodium acetate, starting from solid sodium acetate. So what I want you to do right now is actually pause the video, calculate, do the solve the problem, and press play when you're ready to hear the answer. Okay, so we're looking at making 350 milliliters of our solution of sodium acetate. So we have solid sodium acetate. So sodium acetate, remember, is NaC2H3O2 because acetate has a 1- charge, sodium has a 1+ charge. Molar mass of this guy turns out to be 82.04, 82.04 grams per mole, which we got from the periodic table. If you're not sure on how to do that, go back and review those molar mass videos from the last unit. Okay, so I need to make 350 milliliters of the solution starting from solid sodium acetate, which means that I need to get this into a unit that I can measure, which is going to end up being grams of sodium acetate. So I'm starting out in milliliters of solution. My goal unit here is going to be grams of sodium acetate. Okay, so starting out, I'm going to start out with, so I have 350 milliliters of solution, right? And I know I'm going to have to change it because I have a concentration here in terms of moles per liter. I have to change this to liters. So I know that for every 1 liter of solution, there are 1,000 milliliters, right? Okay, and I know that in this case in particular, for every, I have 1.25 moles of sodium acetate for every 1 liter of solution. And then I know that each mole, so mole of sodium acetate weighs 82.04 grams. Right? And then, so when I put that in my calculator, so 1.25 times 82.04 is 35. So 3 significant figures wise, that's 35.9. 35.9 grams of sodium acetate. Okay, so to make my solution, I need to weigh out 35.9 grams of sodium acetate. The question I want you to think about is, how much water are you going to use? All right, so think about this. Remember that when we add the sodium acetate, that sodium acetate takes up space. So in order to make this solution where it's 350 milliliters of solution, I can't add 350 milliliters of water. I have to add some amount that's less than that. But I don't know how much, and I don't want to calculate it because that's just way too much work. So what I'm going to do is I'm going to say, all right, I'm going to take my 35.9 grams of sodium acetate, and I'm going to dissolve it in, let's say, 300 milliliters of water. And then once it's dissolved, I'm going to add water until I get to a final volume of 350 milliliters. Okay, so I don't know how much water I added, and I don't really care. All I know is that I have 350 milliliters of total solution. Make sense? Okay, cool. So, question at the end. All right, we're going to do some more practice with this in class tomorrow, or next time we meet. But I want you to consider this question and remember that you have to try this in your video notes for full credit for the homework. So you need to make 250, this is similar to before, where we need 250 milliliters of a 0.15 molar solution of sodium carbonate. But I don't have any solid sodium carbonate. I have a 2.5 molar stock solution instead. So I want you to think about it, and I want you to describe to me, using calculations and words, how you would go about making this solution. Okay? Give that a try. Bring it with you to class, and we'll see you next time.